Hello everyone, today with us we have Professor Biresh Joardar from the University of Huston. He was previously a postdoc at Duke University, and his research interests include deep learning accelerators, manycore systems, and machine learning. Dr. Joardar, would you like to tell us a bit more about your background in research?
So I am originally from India, and I did my undergrad from Jadavpur University in ECE. And my focus has always been on designing computers. I like computers from like when I was a kid, and I wanted to learn more. And as from that, like I've started reading a lot in ECE, and from there I just continued, my PhD, postdoc, everything, and even now I'm in ECE. So that's how I ended up in this field. But particularly, I'm looking into what is called reliability. So reliability just means is your computer doing what it's supposed to do? So that's kind of what I work on, and I'd be happy to share with you my work. These are all the different architectures that I'm working on, say smartwatch or smartphone or GPU, this kind of hardware. So what I'm looking into is how do you design hardware for these large machine learning models, right? And also another part of my work is how you can use machine learning to guide your design of the hardware. So sometimes if you study your application, that gives you some clues on how to design the hardware, and hence we have this loop. But primarily, I'm a hardware designer, and so I'm looking into how to make future computers that can handle these big machine learning workloads. So first question, why design new computers? I kind of answered this already. So the answer is, again, huge amount of data. And even in machine learning, these models are getting larger and larger. Like recently, there was ChatGPT. There was a lot of talk about it online. So ChatGPT is a machine learning model that can almost talk to you as if, right? But it's a software. It's a software, but it can almost talk to you. Like whatever you ask it, it can answer it as if it's a human. But those models are like huge. They have like billions of variables and are trained on almost like the entire internet's worth of data. So given that we have these models which are so big and data which is so big, we cannot use our current computers. So we want to have better computers in the future, which would be more efficient. And that is kind of the main goal of my work, how to design better computers. So I'll be explaining my work in two parts. The first one is just how to design computers for machine learning. So here, hardware accelerator just means a computer. So how to design a computer for machine learning. And next, I'll be in the part two, I'll be talking about the reliability side of it. So just a quick intro, what is machine learning? So machine learning is a software which we can train to do some task, right? So say I have a cat picture, lots of cat picture, and I want a hardware, say in this case, this drone, to tell me whether it's a cat picture or not. Now, a drone by itself cannot do that, but I can develop a software which will teach my drone to do that. So that software is the machine learning. So it's similar to how we learn as a human. So say I want to learn how to add, I will take a math class, the teacher shows me how to add, and I learn how to add. So it's kind of the same thing going on here. So you have a software, and we develop the software such that it learns to do some kind of task, in this case, to detect a cat picture. So how to design better computers for machine learning, and what are some of the challenges? Now, of course, computers are super complex. There are like billions of transistors. So here I've listed like some of the reasons why designing a new computer is challenging. The first is system size increasing, which just means that our computers are getting larger with more and more components. Like if you go back 10 years, you have single core CPU, but nowadays you have like dual core, quad core, octa core, right? So the number of cores are increasing every year, and in future, maybe we have 1,000 core system. So the first question, if you want to design a new computer, is how big should your computer be, right? And the next question you have to answer is, what kind of core do you want? So earlier we had like one option only. You had a CPU, but now you have like CPU, GPU, TPU, FPGAs, ASIC. So you have like a variety of choices, and each type of processor is specialized for some kind of task. So the second question you would have to answer is, what kind of processor do you need? And then, of course, you have some application specific questions to answer. So the computer in your smartphone or the computer in cars, those are like very different. So first, you have to see what is your application and what that application needs. Does it need power efficiency, or does it need reliability? Does it need safety? So based on what is the need for a certain application, your design will also change. So these are just some examples of questions that you would have to answer before you even get to the design stage, right? So this is just to show you that it's very difficult to design a new computer. Now, there are like many ways to design a computer, and what I am specifically looking at is what is called in-memory computing architecture. So again, what is in-memory computing? So it's just a new kind of computer. So if you look at any of today's computer, you have a processor where your software is running, and then you have a memory where your data is stored. So the software, whenever it needs the data, it has to go to the memory and bring it and then do the computation on the core. So you have like two things: core, where your software is running, and you have a memory where your data is stored. So in the idea of in-memory computing is, why don't we mix them together? Like, why don't we have like one piece of hardware which is both? So like a two-in-one architecture. It can store data, but it can also do some computation when I want, right? So I am looking into this specific kind of a device called a ReRAM, or resistive random access memory. So again, it's just a variable resistor. So the idea is, by applying some voltage, you can control the resistance of this material. And high resistance means, say, 1, and low resistance means 0. So you can store some binary data in this resistance. So that's the idea. So we are varying the resistance of this material with voltage and storing, representing a binary data. Now, the interesting thing about these devices is, unlike the normal memory, you can use them for doing some math operation like add, subtract, multiply. Like here we have two resistance, and these are voltage. So if you apply the right voltage, you get the sum of your stored value. So you can do addition. So these kind of simple math task can be done with these devices. And that's why it's called a in-memory computing. So it's a one device, but it does two different tasks. It can store data, and you can do some operations, like you can run some software as if. So you have like one hardware which runs your software and stores data in the same place. So that is the kind of computer I am looking into. And this particular architecture is from one of my papers, which is listed here. So here, what we came up with is a computer processor which would have both GPU and this ReRAM. So ReRAM is just the in-memory architecture I was talking about. So what we showed here is that machine learning has like different kind of operations, and ReRAM can do some operations, but not all. So if you want to like support very complex machine learning algorithm like the Chat GPT or some other fancy machine learning algorithm, you need all kinds of computation. So we came up with this architecture which has both a GPU processor and this in-memory ReRAM. And the reason we came up with, again, is to support the machine learning algorithm, which is the focus of one of my work, like how to design computers for machine learning. And this is how one of the way you can do that. Now, for the second part, so this is what is, I would say, the most important part of my research. It's called reliable computing. So again, reliability means, is your computer doing what it's supposed to do? Right? So say you open up your calculator and you type 2 + 3, you're expecting 5, but your computer gives you 6. So that is not a reliable computer. Your computer is doing something wrong. Now, typically, we don't see that, right? If you buy a computer, it works most of the time. So we are used to computers working all the time, but sometimes it doesn't work. And that is the problem of reliability. And this is very important to fix that. Now, when does computer not work, right? So computer may not work in many situations, like in underwater. Like if you pour water on your laptop, it will stop working tomorrow. So water and electronics don't work together. So designing some architecture for underwater application, very difficult. In space also, you have like radiations which can cause damage to hardware. Heat, humidity, all these things are bad for your IC or any computer. So if you are using your computer in any of these situations, you can expect some weird behavior where your computer will not do what it's supposed to do. Apart from those, it may not work if your design was bad. Like say you buy a laptop and the laptop has a faulty, some wire is faulty, right? So if you use that laptop, of course, it will not work because the design is bad. So if your design is bad, which may happen rarely, your computer will not work. Also, when it gets old, it will not work. So if you keep using the same computer for say 5 years, then maybe in your 5th year, you will notice that your computer is hanging sometime or it's not working. So those kind of things happen. So this is what is the problem of reliability. So you have some situations where your computer doesn't do what it's supposed to do. And my research is looking into like, how do you fix that? Right? So how do you fix these situations where when your computer doesn't work as it should? Now, why is this important? Again, in the context of machine learning, say again, I have this drone which can tell me if it's a cat picture. Now, if there are some errors, say you are using this drone in very high heat and heat is bad, so heat can cause some kind of errors. And that what it can do is it can now change your output from cat to dog, even though the input is a cat picture. So you may end up doing the wrong thing, even though you were trained to do the right thing, but because of reliability, you may end up doing the wrong thing. Now, this can be very serious in some cases like medical, right? So in say, if you want to predict if a patient has cancer or not, now say there is cancer, but because of error, you predict there is no cancer. That these kind of applications are very sensitive to reliability. So there you want to ensure that your computer is working all the time. So this is again just some data from one of my own research. So what we did here is we run some machine learning application like these 4 are machine learning application used for object like image processing. Now the blue bar is the case when your hardware is working perfectly, right? So if your hardware is working perfectly, your model works 90% of the time. But if there is some issues, so the orange bar is when your hardware has some issues. In that case, you can see this number drops. So your machine learning model is not working as good as it was doing before. And this is one of our solution that we came up with, which we called weight clipping. The idea is like if the weight is too large, we chop it off. So it's a very simple math operation. And we see that we can make the machine learning model work as good as when your hardware is perfect, right? So even if your hardware is not perfect, we have a way to make it